Well, I'm Matteo Convertino. I'm an assistant professor here in the School of Public Health at the University of Minnesota. And I arrived here through a complex process, I would say. But let's start from the origin and let's try to map that process until here at the University of Minnesota. My background is in civil environmental engineering, and I did my bachelor, master, and PhD at the University of Padova in Italy. And over there, I started by being interested into how fluids, particularly water, move in the environment. And that was really fascinating because if you think about like the Venice Lagoon, it's very important to understand where water goes. And that is useful because we care about, for example, to save the city of Venice, we care about people, but not only that, we care about like the environment itself, to preserve the lagoon, to preserve a lot of fish species, to try to contain, for example, the spread of chemicals in the lagoon. And so, starting from there, because of my advisor of the PhD, I started to be interested more into the biology related to water, into, for example, diseases related to water, and how these processes can actually be somehow universally valid in many different areas that are different than Venice, but still, for example, we talk about the same diseases, we talk about the same species. So I started to understand, to be curious about some universalities, some universal properties that we can find everywhere. Because of that, at the end of the day, translate into just one solution if the processes are universal. And after being Padova, actually during my PhD, I went to Princeton to work with a collaborator, my advisor, and over there I started to explore how, for example, biodiversity is affected by water, the hydrological processes behind things that shape biodiversity. During my postdoc, I went to the University of Florida in Gainesville, and over there I started actually to explore a variety of other things that are related to infectious diseases. But also I try to push myself much farther into some other areas like uncertainty analysis, like complex network, that are topics that are really important for us as a scientist in my field to understand how natural processes occur. For instance, if you consider uncertainty, you are able to explore the dynamic of a complex system in a much larger way, because it's not just one deterministic way in which a system behaves, but there are multiple ways. So the recognition of uncertainty is really important. And they mentioned the topic of diseases, which is something that I'm working right now, and that's why I'm in the School of Public Health. There are many diseases that are really strongly related to the environment where we live. It can be the natural environment, it can be the built environment. I strongly believe that if you consider the environment as the primary driver for the generation of diseases, you can really prevent many of them. Because the medical field is very concerned into the treatment of these diseases rather than in the prevention. And as an engineer, as a person that understands the environment, I'm very much aware that actually a lot of control of diseases can come if we can control the primary source. And that's really basically the fundamental idea behind what I do right now.
An understanding of water seems central. Can you say some things about water?
Sure. Okay. So there is when people think about water, they typically think about rainfall. They typically think about weather. And that's a fairly easy exercise these days because climate model, weather model have been developed since 30 years ago, and they are very accurate, I would say. But water is much more than that, because whenever you think that a drop of water actually fell into the ground, starting from that point, you have, for example, separation of water into surface water, subsurface water, and groundwater that is very deep. And all these things actually affect, for example, where species live. They affect the habitat of many species, from bacteria to a gigantic elephant. And they affect, for example, the propagation of chemicals. They affect the propagation of pathogens. So water, and I'm not just talking about water in the environment, but also the water that constitutes our body, is really a fundamental element to understand and to map where water goes, where water flows, and how much water stays into one single place or maybe travels to other places. So typically, when we talk about water, we try to map where water goes. Here I don't have actually an example of a network where water flows. These are other type of networks, but typically in hydrology, people try to map the networks of the water pathways, because in that way we can trace back, for example, the source of contaminants, the source of many different spillovers of pathogens, where species likely move. Just take, for example, a river network like the Mississippi. The Mississippi is very well mapped, but there are some other situations, like for example in Africa or in Southeast Asia, in which we don't have that knowledge of where water goes necessarily. Or even if you consider the subsurface water, we can't see really well with our eye where water moves, but we can map that through computer models. And so, for example, we can simulate or investigate where this bad agent, from chemicals to pathogen, can spread. So that's really the way in which I see water. Water is something that links everything, and something that produces a lot of good things in terms, for example, of food. That water is certainly something that we need, but also something that can cause harm to people, and so it's something that we really should care and try to map well as much as possible.
So one word for the spreading of things that we don't want to spread is this general word, propagate. And then also there are things like rivers that flow. My picture is that with regard, and I just want to see if there's anything to it, is that with regard to worrying about pathogens, one generally worries about a pretty slow process of diffusion, not flow. Is that right?
It's actually both.
Okay.
Because many times you have a multiple point of diffusion, so you have multiple injection of the pathogens. And yes, sure, you have local diffusion, which is somehow slow in a sense, but you have also dispersal, which happens at much larger scale of the diffusion. And typically, actually, in rivers, that dispersal can be really long in terms of distance and in terms of time. Before I mentioned the case of the Lagoon of Venice. The Lagoon of Venice is somehow limited, but it receives a lot of chemicals that are actually injected into the rivers very far. Take the Mississippi. We are here in Minnesota, we have some industries, we have a lot of agricultural fields. So the pesticides or the chemicals that we use in agriculture, actually we can find them after months in New Orleans. So yeah, sure. I mean, dispersal does not happen quickly necessarily, but it happens, and we can trace these substances from one point to another. And the goal is really to try to contain first of all, the injection of this negative agent into the system, but also to understand how we can somehow reduce the impact for people and animals. That's my view.
So, is it the case that you start to get really worried when the nasty stuff begins to flow?
I would say that I can get worried if there is no knowledge of people of what to do when that happens. Because, for instance, we have Vibrio cholera in the United States, but we don't have cholera outbreaks. Just because we are educated to don't, for example, drink water out of the river, just because we don't use fresh water out of the river to cook or to try to clean our food. But these things happen in Africa, these things happen in Southeast Asia, these things happen in Haiti. That's why we have this cholera outbreak, that's why we have infectious disease outbreak. It's not just about cholera, that was just an example. Because it is very important to educate people, to create also a set of infrastructure that allow people to reduce any sort of impact that this negative agent can cause to us. We cannot reduce all pathogens that we inject into the system. We cannot reduce all chemicals that we use for agriculture, for instance. We need them. There is nothing, there is something to do, but we cannot control everything. So there should be like an education process that tells to people what is good to do and what is not good to do. I think that people are really the primary source. And probably if we educate people, we have much less release of, for example, pesticide into rivers, just because maybe we choose to use some other fertilizer that are more natural rather than chemicals. I think education is probably the primary point.
So, what does a scientist like yourself, what do you discover? I mean, there's this matter, boil water. Don't drink from the river. that goes back to Pasteur. What do you add?
Sure, no, that's a good question that I try to answer myself sometimes. So my research is divided into two things, I would say. On one side, I very much like to discover something that is not yet known, and that is very much a biology question, I would say. We have been talking about water, but the same principle can be applied to a variety of other systems. Like, for example, imagine our human body. Our human body can be actually thought as an ensemble of interconnected parts. And the connection is actually played by this type of networks. Now, this one is a perfectly random network, and this one is a perfectly regular network. In nature, actually, the majority of networks is actually characterized by a network that is something in between random and regular. So it's a combination of these two things. Like you have some gigantic hubs that are interconnected with the majority of other nodes, and you have very little nodes with very few connections. Those networks are actually called scale-free. They lack of a particular scale. You have either very, very big nodes and very, very small nodes. A lot of connection or very few connection. Now, many diseases are actually not well understood in terms of drivers that cause them, in terms of potential public health or clinical intervention that can reduce them, in terms of burden, or even in terms of occurrence at a certain point during a lifetime. So there are some biological questions that we try to understand, and we play with the some biological data, biomarker data. We try to associate this biomarker to some exposure or biomarker of our biology itself, like DNA, if something is really biologically transmitted from one individual to another. So over there is a lot of unknowns, and these computer models that I developed try to investigate that. At a macro scale, for example, we don't know why some species move from one area to another, so we try to understand what's the environmental niche of these species to exist in one place or another. The second part of my research is really try to take that knowledge into an application. If you consider the network of biomarker, when you know that, you can actually try to develop, for example, some nanotechnologies, some nanomaterials that try to control some of the nodes that are not functioning well. Or you try to control the topology of the network. Because the topology of the network can change if we are exposed, for example, to a pesticide, if we are exposed to a pathogen. So if that happens, we can actually control that exposure, that effect in our body. But you need to know the network. Or in a broader scale, since we talk about water, I'm very much actually focused on trying to develop early warning prediction for infectious diseases. Like we have this weather forecast that tell us if it's going to rain tomorrow or not. What I do is actually to develop tools that tell us how many people are going to be sick by cholera, dengue, malaria, stuff like that. All these things are actually related to water. So I can make forecasts of infectious diseases given weather forecast. And that's very useful because if you think about the WHO or the other government entities, they need to know what to do if something happens, when these things happen. You need to deploy vaccine, you need to deploy public health field officer, you need to try to even control the environment. You need to, you can try to limit the mobility of people. You can try to control species that can spread the pathogen. So all these things are really very much applied. And I like to play to do my work in this way. One side is more basic, on the other side it's very applied, but they are interconnected with each other.
So the body stuff is new to our conversation. I understand my body is containing many things that could kill me, which are more fortunately localized in places where they won't. And if they moved, they would. I mean, that's very simple microbiology. Or if they decided to grow, to have a population explosion, they would kill me. But they haven't. They've remained kind of tame and mild. And there are, in the planet, all sorts of things that would do enormous damage that don't, because they're localized or encapsulated or haven't grown as much as they might. Are the similarities important? I mean, is there a way of understanding people getting sick and the United States or Sierra Leone getting sick?
I think you got to the point. It's a very interesting question because that's actually what I really like to do. I'm actually a methods guy. I'm not a biologist. I'm not a physician. I'm not a climate person. I'm an engineer, and I like to find similarities. What I called before actually universalities. If you take our human body, if you take a population, if you take the climate system, there are actually similar processes, like for example reaction and diffusion processes, that can be mathematically described exactly in the same way. And that's an advantage because I can use more or less the same mathematical model to actually try to understand the body, the environment, or much larger system, or a connection of all these systems. So actually what I do is very much using tools that are used in a field that is kind of new. It's called network science. Network science tries to map the interconnection that can be visible or not between elements and try to see how these networks are actually stable over space and over time. So yes, I mean, similarities are really important, and it's also important to see when these similarities are broken, when you started to have a change in the system triggered by something else. People talk about tipping points, or people talk about phase transition. Like, for example, before a disease and after a disease, the network of biomarker that regulate our body is actually changing. And the trick, the interest is to understand when that happens, why that happens. So you have some sort of, you have a break in some sort of similarities that we were talking about. That's actually the fun part. That's what I really like to do.
So, I imagine a body, which if you described it minutely enough would have as many parts as, say, the North American continent described at another level of generality. Mm-hmm. They both have things like rivers. So from the kind of engineering perspective that you're applying to these things, how are these two systems different?
You mean the body and, for example, the North America system?
Yes, or some plausible. I mean, maybe one would want to say Australia, because Australia is at least bounded, and there's no such thing as a North American system, I suppose. But
let me try to give you two answers. The first one is probably more mathematical. Mathematically speaking, if you try to map these two systems on a computer, you see that, well, it depends on what you map, actually. But let's take that you have a network of biomarker. Maybe let's consider all these biomarkers as genes. Yeah, so you have a gene regulatory network that informs you about how your body evolves over time. And on the other side, let's say that you have a network of the water system of North America. If you see them on a computer, they may look different because the topology of the network is actually different. The river network is this scale-free network in which you have a structure that is very similar to like a leaf venation pattern. So it's a tree-like structure, like my hand. Instead, on the other side, the gene regulatory network is more like composed by a lot of multiple hubs that are the most important genes, and also you have many other genes that are less important but still connected. So in a way, it's probably actually the gene regulatory network is more similar to a Facebook network. So they look different. Now, the way in which we describe the processes on the network, that is a very different ballgame. Because on one side, you have actually information that moves from one gene to another. So you have some sort of alteration of the gene expression pattern over time. That can be related to evolution. Let's say, starting from when we are kids to when we become adult, you have a difference in the gene expression pattern. But that gene expression pattern can also be changing because of an exposure. On the other side, for rivers, you have, for example, fishes that move or pathogens that move. So the dynamical processes on the top of the network are different. And that's really the difference. I mean, the things are described mathematically in a different way, but it's not too hard. Again, I go back to the point that I mentioned before. At least mathematically speaking, you have a lot of similarities. So I think that mathematics can be considered like as a discipline in which people try to define a very broad and universal language that use numbers to describe a variety of phenomena that are actually not that different from each other. And that's really the power of our society, I think.
I was, at this time last year, I was in Austria. And I think Austria is a country that reflects constantly on the fact that in about 1940, 41, 42, they began to do really horrible things. Mm-hmm. And then they disavowed those things, and now one doesn't see them anymore, mm-hmm. except in pockets. And it is pretty natural to think about pockets of infection.
Right.
I mean, it's pretty natural to say that when a Jewish cemetery is desecrated, when a rally is held in some little village, that the old racism has broken out.
Right.
And because the country remembers, I mean, the people remember that it swept the country. I mean, I talk to young intellectuals who are very much in your position. Mm. That is, they're saying, how worried should we be? And is the country worried enough about patterns of dispersion of an ideology,
right.
of a kind of cult, of a complex of thought, which when it grabs people is hard for them to shake and becomes natural and becomes in some ways infectious. Mm-hmm. And I'm wondering, there's no reason that you should have thought about this, but I'm wondering if you have.
I did. I didn't mention yet that actually whenever I develop a mathematical model, I always try to work immediately with the stakeholders that are involved in the problem that I'm dealing with. That is not just communicating to them what I'm doing or asking them information, but it's also a way to actually gather stakeholders, people, mental models. What does that mean? So a mental model is actually something that any one of us has that is related to our nature and our nurture. A mental model is a set of knowledge, preferences, bias, attitudes, and believe it or not, actually that can be mathematically described and incorporated into a mathematical model in which you have reaction, diffusion, and dispersion. This may seem sophisticated, but it has a lot of consequences because based on my experience, even if I develop a model that makes early warning prediction of infectious diseases, and I never work with any stakeholders, I never consider what they can do, what they have in mind, that model will be useless. It will never be applied because you cannot force people in developing countries, or even worse than that, to use something that comes from the science out of the blue, and it will never work. It will never ever work. Because first of all, you need some personal engagement, but secondly, you need to incorporate into the model the set of decisions that these people can feel comfortable to take. give the information of the model in the output. You need somehow to include the set of preferences that population have. Because maybe we assume as a Western civilization that education is actually the primary objective of any population. That may be false for other population. Other population may value other things. And any sort of implementation of a control action, for example, to control infectious disease, needs to take into account what people care about, what people are worried about. This branch of science is actually called decision science. It tries to map the decision-making process quantitatively, together with the technical information. And it's a lot of work, to be honest with you, because working with the stakeholders, and in general, the stakeholders are people from the government, the people on the field that can help population, but in general, it can be even a group of politicians, it can be policymakers, it can be people in academia that are not necessarily related precisely to the project that we're working on. It's everyone that more or less have a stake into that problem. It takes a lot of time to do that, but I think it's very important because otherwise our science does not reach the public, does not reach an application. And so yes, I mean, to go back to your Austria example, I think that that spreading of knowledge, that spreading of ideas is really what I'm talking about. Being worried or not, I don't know. I think that I think it's really hard to say when a population should be worried or not about the spreading of an idea, because social systems are much more uncertain than environmental system or biological system like the one that I was talking about. But still, we can try to make some prediction, in a sense, if we should be worried or not, if that spreading of idea is potentially causing something bad or not. We can still try to make that sort of quantitative prediction. But at the end of the day, I think that we are human beings. So the best way to do it is actually to try to involve all the people, try to have a conversation, and try to potentially use this mathematical model that can support the discussion by making some numbers, not just on a qualitative base, but also on a quantitative, in a quantitative way.
So is the judgment then at the end of the day that social systems are enough more complex than water systems or body systems that the mathematics is going to not be so useful?
I wouldn't say that it's totally useless. I would say that the quantification, the mathematical models can help the decision-making process. But obviously, we are people that do not necessarily make a rational decision all the time. We are subjected to a variety of other stressors that may be unforecasted whenever we make the prediction with the mathematical models. And so the best way is actually to use these models in a dynamical way. You should never take a prediction like a fact, if something is happening for sure. A prediction is just something that more or less we believe is going to happen. So on one side, you should be cautious. On the other side, we really can't control everything. I think that we need to be smart in a sense. I don't know. I have a huge belief into the human intelligence, into the human brain. And again, I think that mathematical models are just one instruments that can help us. But at the end, we have also our brain, and we have other people to deal with. So it's a combination of both. It's a combination of both.
So, if I'm understanding you right, a bunch of what you do is to try to explain to stakeholders what the mathematics suggests about what's likely to happen and what's likely to be necessary to prevent certain bad outcomes. And then to try to get the stakeholders to translate that into actions that they can actually do. Is that the picture?
Yes, overall it is. There is actually a part that is really quantitative. So for instance, sometimes we gather stakeholders, we ask them questions directly or indirectly. Directly can be really just asking to people, do you care more about the environment or you care more about health? Do you feel more comfortable to use vaccines or use some other hygiene and sanitation alternatives? That's out of question. Or some other times actually we let them play a video game, and that video game simulates how the infectious disease evolve over space and over time, and in the selection of the action when they play the video game is actually a manifestation of their mental models. We take that material and we translate that into numbers. So for example, I can actually tell from the answer of a person or from the gaming of a person how much that person care about the environment versus health, how much that person care about money versus the environment. It's a quantification of trade-offs. So at the end, my model prediction, that is not just how many cases we're going to have about an infectious disease, but it's also what to do and when to do a particular control for a disease, let's say vaccine, education, hygiene and sanitation, when it's going to provide a solution that reflects stakeholders' opinion, stakeholders' mental model. The solution is never the same for everyone. Let's take cholera. There is not just one solution that is valid everywhere around the world for two motivations. One, because the processes, the biological processes related to the spreading of cholera may be different, but also because the stakeholders are different. They carry a very different set of values, a very different mental models. To make a very simplistic example, and that's actually the classical example in decision science. Let's imagine that we need to buy a car. You and I carry a very different set of values, right? So for example, I value more high static, I don't care about money. You may have a very different set of values. So with the same resources that we have, and maybe with the same setup, with the same life, let's imagine that that's the case, we actually make a very different choice, right? Because the utility that we attribute to the criteria that we value different is different. So that's really a very simple example. And that's what we try to map whenever we have a lot of people that needs to make a decision about a complex problem.
So you have a set of numbers and a model that says what a given pathogen's going to do in an environment, and say predicts that a particular string of villages will be in danger in a particular point of time at the best. And then you have another set of numbers and a model that says how these villagers are likely to regard various proposals that are made for changes in their ways of doing things to prevent this pathogen from doing the damage it could do. And you hope that when you put these two models together, you get something you can do
Right.
that actually makes sense in terms of what you're predicting will happen.
Right. And another thing is that actually many times is actually probably a good way to do science and practice to try to shift stakeholder preferences if they are clearly wrong. So for example, I don't know, before we were talking about education, if we find out that for any of the stakeholder, education has very low value, well, maybe consciously I try actually to change that. Because we certainly we should accept values of anyone. That's a form of respect, and that's a form of something that probably we can't control completely. But because we are educators primarily, well, we are researchers as well, but we are also educators. We also try to actually inform people about the best course of action. I think it's a good, at the end of the day, actually, probably that's what we do with our students. I mean, we try to teach something because we try to shift their set of values that maybe can be wrong somehow. I don't know. It doesn't need to be wrong or correct. Maybe we try to change this set of values towards something that produce a much better outcome for everyone.
So is there a mathematics to that? I mean, there has to be. There's a mathematics to everything, but is anybody worrying about it? I mean, we think about pathogens. We understand what they do, why they harm people. And then if you go to southwest Minnesota, where I did spend some time, you have people who are eating very badly and dying very soon and having very uncomfortable lives, living next to people who are eating very well, remaining very healthy throughout their lives. And these are two different ideas about food,
Right.
and presumably they propagate.
Right.
And there are things like rivers that carry them. And there's also simple diffusion. The neighbor kids come over and eat and like what they eat. But I mean, it's sort of a difference. I mean, there isn't in a natural system, I mean, one doesn't, unless one takes Chinese medicine seriously, one doesn't think seriously about the diffusion of goodness. One thinks about the diffusion of pathogens.
No, I agree.
But in a community, in human communities, we can identify, however value-free we might want to be, on some pretty simple criteria, we can identify healthy connections. And the question is, having identified those, can we study those with just the same mathematical models?
Yeah, there is one famous study of a colleague of mine, Nicholas Christakis, in Framingham, Massachusetts. He published in 2007, I believe, and there were further papers, a very famous study because he actually mapped in the Framingham community the network of family ties and friendship ties, and this is show clearly how the spread of obesity was actually related to how people were actually influencing each other about food consumption, where the food was not high quality, but it was like fast food or stuff like that were making actually people fatter and fatter. And that was actually probably one of the first papers in which people say, hey, you know that this spreading of behavior is actually very much related to the people that we have around. I mean, it's not a novelty. I mean, we know that. But the way, you see, many times quantification provide numbers. And if you provide numbers, you are able to tell how much something influences something else. right? It's like if I say, if I invest $10 into this stock, how much revenue do I have after 5 years? Quantification is not pretending to claim what we know already. Quantification is useful for trying to really understand how much a certain factor affects another. In that case, he actually, this colleague of mine, he mapped the network and he said, okay, how much family tie or friendship tie is important for the increase in obesity incidence. How much certain type of food are actually responsible for that increase in obesity incidence. It was a very quantitative study, using some novel tools, using some new visualization, pointing out exactly what you said. Now, how to take that science into something that people can use? I don't know, I would say that, I mean, at that level, I probably am not really the best expert to provide any opinion, but I think that we have some people that are, like, even whenever we make an advertisement, I don't know, policymakers or people that are sociologists, someone, schools, education, can really try to communicate those messages out to the public.
Well, I mean, one of the articles that changed my life was the piece that Malcolm Gladwell did some years ago. I think about a woman. I think her name was Doris Weisberg. Mm. It's the piece about a woman who had her fingers in so many pots, had so many relationships that she ended up being the connecting point for thousands of people. Mm-hmm. She was the node of an incredible system. Mm-hmm. And when I read that, I got very happy because I thought maybe human systems with this kind of node in them are accessible to very fast transformation. Yes. Through those nodes. Maybe they're different from natural systems which don't have so many pieces coming together on a few key actors. I mean, maybe it's not a matter of diffusing an opinion or an insight or an attitude through thousands of people, but broadcasting it to the Dorises of the world.
Sure. No, well, yeah. I mean, the identification of the hubs, the most important node, is crucial. Because, from them, you may have the generation of bad or good things. So if you take, for example, the case of Framingham in Massachusetts that I was giving before, in that case, you didn't really have any hub, essentially. You have multiple communities and you have multiple hubs in which this behavior-related disease, obesity, related to food consumption, was actually spreading. So in that case, you didn't really have a hub. And probably the control has to be more broad. That's one example. But in the example that you mentioned, you certainly have one person that is at the core. Now you need to be careful because that person may actually spread something very negative and that influence everyone else very, very quickly. Like, I don't know, let's imagine what happens during, before and during the Second World War. Adolf Hitler, he was the hub of the whole Germany, the whole Nazi community. He was the core. They took him out, end of the war, right? But on the other side, you may have someone that truly changed the way in which knowledge, the way in which action are made. Very typical in science. Take Albert Einstein, take Leonardo da Vinci. They were like very special node, somehow tied to many other things. And yeah, sure, maybe with some delay over time, they made a revolution in a field, in the whole world.
So do natural systems, we think about bodies, we think about continents, do natural systems have this kind of crucial node? I mean, places that settle matters, that disperse information out that broadly?
Some of them, not all of them. If you take a river, the biggest node is actually the outlet. For the Mississippi, is actually the delta of the Mississippi. New Orleans is in terms of, if we quantify, for example, the amount of water that exit a particular point, that's actually the size of a node in the river system. Actually, that's New Orleans in the case of Mississippi. So you see, in that case, you cannot really do much because you are already at the exit. You need to be careful about smaller nodes that are upstream, because those are the nodes that essentially determining what is entering the system and at the end reaching the end, the biggest node. So it really depends on the system. Let's see, other biological system like the DNA, the gene regulatory network. In that case, you have multiple hubs. It's not just one. So you have multiple hubs to take care of. It really depends. But to make you feel more comfortable, is that actually in nature, they can be man-made system or natural system. There are actually just 4 types of network that exist. You have the perfectly regular, perfectly random, and after you have the scale-free and small world. Scale-free is the one in which you have just one hub and all the others are small. A small world network is in which you have multiple hubs and others small. The case of a small world network is like Facebook. You have some people that are really highly connected. They have a lot of friends, and many others that have relatively few friends and not many connections. So in the world, you don't have such a huge variety of network. I would say that we can characterize network into 4 types. So more or less, again, we are, our job is easier because nature is not random and it cannot escape different topology. You cannot just make a new network that is totally different. It doesn't exist, mathematically speaking.
So presumably with regard, you have some control with the network you're producing, if you're producing it.
Sure.
To make it fall into one of those 4 kinds.
Right.
I mean, if I say, I'll give you 1,000 people, you can organize them, you can produce one of those balls, right?
Sure.
You could produce all of those balls.
Sure.
By, stringing telephone lines or making introductions or forming clubs.
Right.
So I have 1,000 people for you to experiment on. They're all volunteers. And you can make them into one of those, any ball you want. So, is there one ball you would make them into?
Yeah.
Do you like them? Are all the children the same for you? Do you like them all equally well?
You see, the shape that I would choose is dependent on the objective that we have. If the objective is going to be if the objective is to be very resilient, that means under any sort of external influence, I wanted that my network maintain a certain topology. And probably if I wanted to maximize the spread of information, I would choose that small world network, like Facebook. I think that it's a very bad idea if you have just one big network and everyone else is small. Because in that way, someone can kill the big network, the big node, and everyone else dies. That's the case of the power grid system that we have in the United States, or or in the majority of countries worldwide. You don't have just one big hub that delivers energy. So it's very wise to select multiple big nodes and everyone else is small. So it's a kind of more distributed system. I'm trying to imagine when is the situation where I would choose just one big node and everyone else is small. I don't know, maybe if I build my own company. I wanted to be the big node and everyone else is small. I don't know. But that's more about like a very organized, the case in which you have one big node and everyone else is like falling downstream. It's when you have a very well constructed system in which you try to have a very structured way that optimize a certain function. And actually, probably the case of a firm, the case of an industry is actually a good example. You have the CEO, and everything else is very well structured, like a dendritic network.
Apple.
Yeah, kind of. Yeah, Apple.
I mean, and this incredible control of design.
Yeah. It's a very well controlled. It doesn't need to be bad. It's actually very good. You need that organization. Instead, when you have Facebook, you don't need an organization.
And the other two?
Well, I think that regular does not really make too much sense unless, actually, you see, this one is a rock. The question for you, is this on a network? You would say no, because at this scale it seems a solid. But is truly a solid? Actually, I can tell you that if I zoom in, I can actually try to map the network of chemicals that bond the elements that form the rocks. Or even if you consider the microstructure here of all the single minerals, actually you have some porosity, you have some empty spaces. And actually this regular network is very much formed in highly organized system that evolved over a geological time scale. So essentially this one is somehow, in order to form this one, you need to have long evolutionary time frame. And this one becomes really very stable. And it's really hard to modify this. It's a rock. That's why they are so hard. That's why we can throw them away and the network does not change. But typically, what is regular in our life? Nothing much. Maybe we don't have enough time to evolve into such a regular structure. And random is random. No one wants a completely chaotic system in which we don't have any control over anyone, right? So I would say that these two types of network are probably the least common. And I wouldn't choose them myself. That's my take.
Well, I'm not, the random one I'm not so interested in, but what about that other one? The one that's the rock. What are its characteristics? What is it that distinguishes that one?
I think here I should introduce another concept. So you see, right now we see this rock as a solid, just because the scale at which we see the rock is the scale of our eye somehow. We can take it and we don't really clearly identify any node, any connection. And by the way, not all the networks are visible. I talked about before the network of chemical the chemical interaction between the atoms that form the minerals here. That's not visible. You need a microscope. They are chemical things. Or the gene regulatory network. It's not something that we can see. We know that one gene transmits information to another gene. And so that spreading of information is a connection, but we can see with our eye. So certain network can be seen only at very small scale or very large scale. They may not be completely apparent in the way you may think about. Going back to water, groundwater networks. We don't see them just because we cannot dig the soil everywhere, and plus if we dig, we essentially destroy that connection, right? But we have flows of groundwater moving from one place to another. So I mean, trust me, this one is a network. We just don't see it as a network because our scale of analysis is too big.
So your thought is, I mean, the answer to the question about what you'd produce is you don't, for most purposes you can imagine the random one wouldn't make sense. And it takes far too long for that thing that represents what's going on in the rock to take place. So essentially we have two choices.
Yeah.
Two choices in terms of what we bring about. This sort of hub and spokes kind of thing. And the distributed, Facebooky sort of thing.
Sure.
And of those two, if you want resilience, go with the Facebooky kind of thing. And if you want to increase resilience in a system, make it more Facebooky.
Well, but not too much. I don't think that we should exaggerate to make too many hubs, because in that way you lose control. So distributed, but not too much distributed. But again, it really depends on the objective that you have.
Yeah.
You see, topology is one piece of the decision. By the way, these four types of network are actually called, they are called topologies, four topologies. Topology is a branch of mathematics that is more broad on geometry. Topology wants to find the similarities that you asked me before.
Mm-hmm.
Different systems, what are the similarities? They are called topological similarities, not geometrical. It's not just about the choice of the topology, it's also about a choice of where do we need to put the hubs. Think about the power grid. Where do we need to put the biggest energy generation places? Minnesota, Florida, Michigan, I don't know. You need to understand the shape of the system, you need to understand where the population is, you need to understand where climate can destroy the system. You see, it's not just about the topology, it's not a trivial choice. You need to say, well, okay, what's the best position of those hubs to be more resilient?
I see. So systems are going to be some kind of compromise between these two.
Yes, exactly.
And the question that you'll keep asking is, what sort of compromise in order to achieve a particular purpose?
Yes.
Thank you.